Okay, thank you, Misha. So I'd like to first mention that this work is actually going to appear as a paper in Communications on Pure and Applied Mathematics together. It's a paper together with Hao Yang, who sits in the back there. And this paper is actually dedicated to the memory of Partha Niyogi. And as you'll see, this work is rooted in Partha's work, especially what he did with Misha and others on Laplacian eigenmaps. Some of it we've heard in previous talk. So before I go into the theory, I would like to start with a motivating example. It's a problem in structural biology where we try to find the three-dimensional structures of molecules. So these are molecules that cannot be crystallized. So instead, what people do are they're freezing the molecules in a very thin layer of ice. So the ice layer is so thin that if you look in the vertical direction, you would see at most one molecule. So they don't have enough room to be in that position. And then you take pictures or projection images using an electron microscope. So you shoot electrons at the ice layer, the specimen, and the electrons go through the ice layer and through the molecule, if there is a molecule. And the pixel in the image just corresponds to the line integral of the electric potential created by the molecule plus some noise. Now, so this is very similar to classical computerized tomography, where you try to find three-dimensional structure, let's say, of the density map of the brain of a patient. And in CT, the patient that goes into the CT machine is being told not to move during the imaging process, so that the imaging directions are completely registered, they are known to the machine. But in cryo-EM, the imaging directions are completely unknown to us. So at the moment of freezing, each molecule just picks some random and unknown 3D orientation. Also, the positions are unknown to us. And so it's quite more complicated to figure out the structure, because on top of that we don't know the structure, this is what we try to find, we don't know the imaging directions. So it's quite more complicated than just computerized tomography. So the goal is it's like an inverse problem. Given the images P1 to Pn, so assume that we have n images, we want to find the structure, we want to find the potential function phi. And if we can get from the images to recover the rotations, the unknown rotations corresponding to the images, then we can apply classical computerized tomography methods. And today I will focus just on one particular step in the pipeline, the algorithmic pipeline of finding the structure. And so before we do that, let me just illustrate again what I mean by find the structure. So suppose you have 12 such projection images, and what you try to figure out is the structure. So you don't know the structure. But from unlabeled images like this, you want to find the structure. So here you can even clearly see that we have a Mickey Mouse here, just by looking at some of the projection images. But with real life images, the ones that we get from the experiment, it's kind of hard to see that there is even a molecule here. So these are images that we got from the Sigos lab at Yale Medical School. And so these are real microscope images. And I hope that you can see that the portions near center are slightly brighter than near the edges of the images. And that's actually how they choose particles. So first one is to solve some image segmentation problem that you have a large micrograph, let's say 4,000 by 4,000 pixels, and you have to identify and take electronic scissors and actually cut small boxes. But suppose that this has already been done for us. Now, from this kind of noisy images, we want to find a structure. So the first idea in cryo-EM is to do some kind of averaging. That is, it's relatively cheap to take images, so data sets can range from 10,000 to even 100,000 images. And if we can average images that are taking at roughly similar viewing directions, and then we can denoise the images and maybe do something with it. So just to show that it's possible to get a structure, I want to show you a movie done by Dan Hui, who also sits over here. And let's see the movie. So this is actually a reconstruction from images that you see here. So what you see here are two volumes superimposed, one in yellow, one in white. So the yellow one is the ground truth. We know the ground truth because in 2009, the Nobel Prize in Chemistry was awarded to 3 people that actually got the structure of the ribosome, and this is one of the subunits. And in white, you see our reconstruction. And I hope that you can see the resemblance between the two structures viewed from different angles. And this is actually from the noisy images. But there are some features that you can also see that are missing here. And so this is about something that we did about a year ago. I hope that now we can actually do better. So going back here, what is class averaging? How do we denoise the images? So, so this is from a simulation. I took just a clean volume. This is the projection image in one particular direction. This is the same projection image, but added to it is a Gaussian white noise at not so high level of noise, so you can actually see the features in the image. Here is another image at just rotating this by 90 degrees and adding a different realization of noise. And suppose these are two images out of a collection of, say, 10,000 images. Can you really identify that these are taken from exactly the same viewing directions, but different in-plane rotation of the camera, and then do the alignment, in-plane alignment, average them, and get a higher quality image? So that's a class averaging problem. And what people do now in order to solve this problem, they define similarities or dissimilarities between images that are rotationally invariant. So we can take two images, say Pi and Pj, and try to register them. That is by optimizing over the rotation group, SO2, just in-plane rotations, and you try to find the in-plane rotation that optimally aligns the two images. When you find this rotation, then the distance between the two images after they're being registered, you call it the rotation invariant distance between image I and image J. So you can play this game between any pair of images, I and J, and you get a matrix of dissimilarities. And then you can say, so naively you can say, okay, I would like to do some nearest neighbors averaging. So for every image I will find its neighbors, do alignment, and just average them to get a higher quality image. Or you can do even better by doing some clustering algorithm. For example, what is being done today in the field is K-means algorithm. And of course, if the images are not centered, you can also optimize over the Euclidean group and add a bit of translations. But at the level, so this algorithm works fairly well, but not so much at the level of noise that we encounter with the real experimental images. So the question is, can we do even better than just apply some clustering algorithm on this dissimilarity matrix? And I would like to show you now that there is some information that we actually threw out and haven't used so far. So really, the way I think about the class averaging problem is that we have a graph where the nodes of the graph are the images, and you can put an edge between any two images if, let's say, the rotation invariant distance is smaller than some threshold. So this graph, if the images were clean, this graph should be a neighborhood graph over the two-sphere. The two-sphere, because every image can be characterized by just the viewing direction. And we have rotation invariant distances, so 1 degree of freedom, the in-plane rotation, we don't need to care about. So to the left, I just drew a ring graph because it's hard for me to draw a neighborhood graph over the two-sphere. But we know that images are not clean, so we have lots of outliers. What I mean by outliers, they're basically shortcut edges. So two images that correspond to completely two different viewing directions, but you think of them as being similar because somehow actually the noise aligns well and not the signal itself. And so what we'd like to do is actually to detect the good edges from, let's say, from the shortcut bad edges. So one way that one can go about this problem is, say, to count triangles. So for example, you expect that a good edge will be a side of many more triangles than a bad edge, for which you need to find like two other random edges that will form it into a triangle. This is related to what we heard before about taking the Laplacian squared. But in the cryo-EM problems, there is actually more information that we can use, and we can actually count only what I call consistent triangles. So there is a triplet consistency relation that needs to hold for good triangles, and this involves the angles that align the images. So when you take two images and you solve this optimization problem of aligning them, you not only get a distance, but also an optimal rotation that aligns them. And so if you have three images that you think are taken from the same viewing direction, then the sum of the three rotation angles should be 0 modulo 2 pi. That is, when you rotate image I to image J, and then from j to k, and then from k to I, the sum of the three rotation angles should be approximately 0 modulo 2 pi, or in transformation, we can just write that the multiplication of the three transformations should be approximately the identity. And so we should really count only triangles that satisfy this consistency relation. But then one can ask, okay, but I can also look at cycles of length 4, length 5, length 6, and so on. How do I make all of this in some systematic way, mathematically systematic way? And this is where vector diffusion maps comes into play. And so the framework is that we have a weighted graph. We have nodes, I, j, and so on. We have edges that connect nodes, and we have some non-negative weight associated with the edges. But on top of that, we can also endow the edges with transformations. So we endow, let's say, the edge between I and j with a transformation OIJ, an orthogonal transformation. In the Cryo-EM case, it is just a 2x2 rotation matrix. But in general, we can talk about other problems. And the question is this extra information, extra knowledge of transformation that we put on the edges can actually help us in order to organize this graph, let's say, do dimensionality reduction, to embed this graph in a low-dimensional space, or to define better metric between the data points. So the answer is yes. I'll show you how to do it. But first, I want to show that this construction is not very particular to the Cryo-EM case. So of course, you can do it for any data set of images where you can try to align them and register, or you can think about three-dimensional shapes that you can align and so on. But actually, you can build such graphs endowed with transformations in a very general framework of manifold learning. So a very quick recap. So we have n data points. So here I'm using n, not m. And so there are points in a high-dimensional space, Rp. But they're not just scattered around space, but they're actually satisfying the manifold assumption that they are drawn from a low-dimensional manifold, say a d-dimensional Riemannian manifold embedded in Rp. So d is much smaller than p. And now let me show you how you can construct the transformations, the OIJs in this particular case. So first, we do it in just two steps. The first one is local PCA. So what you do in local PCA, you take some data points, say xi, and you look at its nearest neighbors, say points that are in some small neighborhood of it, and you do PCA for these points. And by doing PCA, what you're going to find is an approximation to the tangent space, to the manifold at this point. And so you can organize this basis in a matrix OI. So I is just the ith data point. And OI is a P by D matrix. So it's a thin long matrix. And this, let me fix it. You can keep on reading. And this thin and long matrix has D columns. So the manifold is d-dimensional. And P is the ambient space dimension. And it's an orthonormal basis. So OI transpose OI is just the D by D identity matrix. Now, if the manifold were flat, then the basis that I will get at every point. So now I can play this game, local PCA game, at every point on my data set. I play it at I, j, and so on. So if I take, say, two neighboring points, I and j, and I get the matrix OI, and I get the matrix OJ. And now I can look at the matrix OI transpose OJ. If the manifold was flat, then I have two bases that span the same subspace of Rp. And this matrix OI transpose OJ would be a D by D orthogonal matrix. But in general, when I have curvature, when the manifold is not flat, then this matrix will not be orthogonal, but I can still find its closest orthogonal matrix. And like we saw before, this can be done very easily using the SVD of the matrix OI transpose OJ. So between any nearby points, I can easily form for you a matrix OIJ, which is a D by D orthogonal matrix. So regardless of the Cryo-EM case or comparing shapes or images, you can just work with any point cloud data and build this graph endowed with transformations. Now, in the manifold learning case, one can actually show that this matrix OIJ approximates an operator that you learn about in differential geometry. It's called the parallel transport operator that tells you how to transport vectors from one tangent plane to the other by sliding them along the geodesic that connect them. So now what do we do with the weights and transformations? So what we do with them, we just form a big matrix, just like in the Laplacian eigenmaps framework. So we build a matrix of size nd by nd. So again, n is the number of points, d is the dimension. And so, but I really want you to think of it as an n by n block matrix where the blocks are of size d by d. So if there is an edge between point I and point j, you're going to put in this block the transformation Oj and scale it by the scalar affinity Wij. And if there is no edge, just put the zero block. So I could have omitted this line, but I just wanted to notice that it is usually a very sparse matrix. So it's easy to do computations with it. And just like in Laplacian eigenmaps, we're going to also define a diagonal matrix with the weighted degrees. But this matrix is, again, an n by n matrix of blocks of size d by d. So I'm going to multiply the weighted degrees by the identity d by d matrix. So we have d and s. And now I'm going to look at the matrix D inverse S. So I want you to think about this matrix as an averaging operator for vector fields over your data set. So let's see what it means. So we can take this matrix D inverse S. It's a matrix of size nd by nd. So I can apply it to vectors of length n times d. So for example, the vector v is of length nd. And let's regard it as a vector as n vectors of size d. Each such d tuple, think of it as a vector in the tangent plane at node I. And when we apply d inverse S to v and see what happens at node I, it's really a weighted average of the following. So we look at all our neighbors. So we are I. We look at our neighbors, vj's. We parallel transport them to I, to our frame. And we do weighted averaging. We multiply by Wij, sum, and divide by the weighted degree. So it's an averaging operator for vector fields. So while in the Laplacian eigenmaps and diffusion maps, one looks at diffusion processes or random walks and an averaging operator for functions over the data, here we're doing a random walk or a diffusion process for vector fields. Hence the name vector diffusion. And so this is a very key operator to consider in this framework. So now what do we do with it? Okay, so I defined a vector diffusion process. But now what we really want to do is somehow, let's say, to embed the graph in a low-dimensional space. So what do we do? So let's read together. So in the vector diffusion map framework, we define the affinity between node I and node j by considering all paths of length t. So t is some parameter that connect them, but instead of just summing the weights over all paths, we sum the transformations. So in diffusion map or Laplacian eigenmaps, we're going to embed two nodes, I and j, as nearby points if there are many paths that connect them. If there is high affinity, we define high affinity between them. If there are many paths connecting them, we're doing path integration. Here I want to do path integration for transformations. So for example, if we go back here, let's consider, let's say, these 2 points, I, and let's say this point. There are 2 ways we can get from here to here in, say, path of length 2. Let's say by going in this way, or by going in this way. But instead of just adding the affinities associated with the path, we can consider the different transformations that we get. Say Oj times the transformation that we have here, and the transformation associated with this path. Now, the transformations may agree with each other, or they may disagree. And in order to see the amount of agreement, we want to just add up all the transformations together from all possible paths. And if they agree, we're going to get some very big matrix, large matrix. And if they don't agree, we're going to get lots of cancellations. So mathematically, in order to figure out how much agreement we have, we do the following. So we add this matrix D inverse S. By raising it to the power of 2t, we're going along all possible paths of length 2t. And we're looking at the ijth block of it. And now we need some matrix norm to see how large is this matrix, to see if we had lots of cancellations or not. So I'm going to choose the Hilbert-Schmidt or Frobenius norm squared for this matrix. And this matrix D inverse S like we've seen before, it's similar to the matrix D minus half, S D minus half. So this matrix S wiggle is a symmetric matrix. And what we are going to see in the next slide, that this affinity, this non-negative number, is actually an inner product in a Hilbert space. So we have this matrix S wiggle. We said it's a symmetric matrix, so it has a complete set of eigenvectors, n d of them, and eigenvalues, real eigenvalues, that we can order in decreasing order of magnitude. And the I-chase block, we can just write it using the spectral decomposition, using all n d eigenvectors. And after we raise it to the power of 2t, we just have to take the eigenvalues and raise it to the power of 2t. So here's why I actually chose 2t, just to ensure positivity, because I don't know if the eigenvalues are positive ahead of time. And so think of VLI as the realization of the L eigenvector in tangent plane number I. So it's just a d-dimensional vector. And now we want to compute this Hilbert-Schmidt norm squared, so I need to take this matrix, multiply it by its transpose, and take the trace. So after multiplying by itself, I'm going to get a double sum. So I'm summing over L and R now from 1 to ND. The eigenvalues are going to be multiplied. And after taking the trace, what you see is that you need to multiply these two inner products. So what you really do is you look at the ith node. You have all the realizations of the eigenvectors at this node, this tangent plane, and you take their inner products, all possible inner products. Inner product is very natural here because it's invariant to the choice of the basis. If you rotate, let's say, if you use MATLAB and MATLAB gave you a different basis, it will not change the coordinates that you get here. It's invariant to this choice. And what is nicer is that from this simple formula, you can see that you can write the affinity as an inner product between two vectors that we call them the vector diffusion map. So what is VTI? VTI maps node number I to a set of coordinates. So there are many coordinates here, say almost ND squared coordinates, where the LR coordinates is just the inner product between the L's eigenvector in node I with the R's eigenvector in node I, and you scale them by the multiplication of the eigenvalues raised to the power of t. So we have an embedding that takes nodes I and gives you a set of coordinates, and we call this embedding the vector diffusion map.
Go back to just the dimensions. So you have d dimensions. That's the dimension of the manifold.
Right.
So why do you have n times d? Why is L and R going between 1 and n times?
So S wiggle is a matrix of size ND by ND. So it's having ND eigenvectors.
These are the vectors of the big matrix. That's
Right.
the local PCA vector.
Right. Think of them as eigenvector fields over your data set. So that's the vector diffusion mapping, but now that I showed that it's actually an inner product in a Hilbert space, it means that you can easily define distances. So we defined the squared vector diffusion distance as the inner product of the vector diffusion map at node I with itself plus j with itself minus 2 times the inner product of I and j. So now we have distances between nodes that actually take into account all the consistency between the transformations. And like we saw before, there are many different possible normalizations of the matrix S that can be applied also here. And in particular, one can easily show that all eigenvalues of the matrix are going to be between -1 and 1. And this is particularly useful because this means that in reality, we don't really need all ND eigenvectors because there is a very quick fall-off of the eigenvalues, especially once you raise it to the power of t. So in order to approximate the vector diffusion distances, you only need the few top eigenvalues and eigenvectors to get good approximations for the distances. So here is the application to the class 74 in cryo-EM. So it's like the before and after picture. So to the left, you see a result of a simulation that we did with 40,000 images at quite a high level of noise. The SNR is only 1/64. And between any two images, we can, so there are 40,000 images. We look at the 40 nearest neighbors images of every image. And between any such images, we can see what is the viewing angle between them. And as you can see, there are many, many outliers. So all the way to 180 degrees, meaning that these two images with completely opposite viewing directions are actually identified as the same image. And after you apply the vector diffusion map framework, and now you take only the 40 nearest neighbors in terms of the vector diffusion distance, you can see that many of the outliers have been completely removed. So here I think like something, there is a fat tail of 50% of the neighbors, say beyond 20 degrees, but here there is only like a tail of only say 5% of the neighbors. So what we can prove in terms of the theory is a convergence theorem. So similar to theorems that Partha had with Misha and others, that the Laplacian eigenmaps really converge to the Laplace-Beltrami operator, and later when you have some non-uniform distribution of data points over the manifold, it converges to the Fokker-Planck operator. We have a similar convergence theorem for the vector diffusion map construction. And so if you take the weights from a kernel function and define the transformations, the OIJs, just like I showed you with the local PCA and the alignment step, then this matrix, after you subtract the identity, converges in the limit that the number of points goes to infinity and epsilon goes to 0. It converges pointwise to an operator called the connection Laplacian. So the connection Laplacian is again a second-order differential operator that one can apply to vector fields, tangent vector fields over the manifold. And so this explains why I call it the vector diffusion map and the connection Laplacian. And again, one can apply different normalizations and get even this kind of connection Laplacian also in the non-uniform case. So just to illustrate, for example, when you sample points from spheres of different dimensions, and you get multiplicities of the eigenvalues that I hope that you can see are in agreement with what you get from say just doing the calculation. You can use your representation theory in order to calculate exactly the multiplicities of the connection Laplacian. Another cute application is that the connection Laplacian allows us very easily to determine if the manifold is orientable or not. So for example, if you look at the Laplace-Beltrami operator, it's very difficult from its eigenvalues and eigenfunctions to determine if, say, I'm looking at orientable manifold like the sphere, or I'm looking at a non-orientable manifold like the Möbius strip. But using this construction, if you just look at the matrix whose entries are the determinant of the OIJs, it's very easy from the top eigenvector to see if the manifold is orientable or not. It's going to cluster very nicely to two values if the manifold is orientable, but in the other cases when the manifold is not orientable, like in the Klein battle or the projective planes, then you get values all over the place. And it's also very easy to find the embedding of the double covering of the non-orientable manifold by just looking at a matrix double the size. So just take this matrix of the determinants and take its chronicle product with 1 minus 1 minus 1, 1. And then but from the eigenvector, so you get an embedding. So these are using the top three eigenvectors of this matrix. In the case of RP2, you just get the sphere S2. In the case of Klein battle, you get the torus. And in case of the Möbius strip, you get the cylinder back. So I would like to summarize now. So what I showed you is a generalization of diffusion maps and Laplacian eigenmaps that goes from functions over the data set to vector fields, and basically using the heat kernel, not for functions, but actually the heat kernels for vector fields. You can think of it as a way to globally connect many local PCAs. So I think that all of you sitting here realize the importance of PCA in data analysis. And what I showed you here is actually a way to transport vectors from one local PCA to another over your data set. We define a metric, a vector diffusion distance for our data points. You can generalize it to higher order Laplacians for point clouds. And for example, like we did for vector fields, you can go to one forms, two forms, and so on. But you can also think of other Laplacians, like the Hodge Laplacian. It's a way, it's a baby step towards revealing the topology of the data. Here, we just did orientability, and we will hear much more about topology in later talks this conference. And it's a useful tool to perform diffusion over orbit spaces. So whenever you have a quotient space where you're quotient with some group of transformations, then you can use this group of transformations to relate data points. And the other applications that I haven't discussed. So the final two slides is just the three references where you can find this material. So one is the paper I mentioned at the beginning. Another one about the application to find the rentability and to the class averaging problem. And I would like to acknowledge the following people. So Hao Tiang. So actually, the first three are actually here. So Hao Tiang and Jane and Lan Hui are students in Princeton. Hao Tiang is postdoc now. Ronnie Adani from UT Austin. Previously was an instructor in Chicago. Yoel Shkolnitsky from Tel Aviv University and Fred Sirius from Yale Medical School, who provide us with the data and the funding agencies. So thank you very much.